Today we are going to discuss about some of the results of electrostatics of conductors. The following are the conclusions or result that can be made from the electrostatics of conductors. So the first one is inside a conductor electric field is always zero. Let us consider a conductor. This is the conductor and it is placed inside an external electric field, but electric field inside a conductor must be zero. So what happens actually is this external electric field causes electrostatic induction, and we already studied what is electrostatic induction. Since it is conductor, large number of free electrons are there and positive ions are there. There will be a shifting of the free electron and positive ion induced by the external electric field. The positive charges will be shifted in the direction of electric field and negative charges will be shifted in the direction opposite to the electric field and create an internal electric field EIN, and the shifting of electrons and positive charges will takes place till internal electric field is equal to external electric field, and that produces net electric field inside the conductor. E is equal to E external minus E internal, therefore E external is equal to E internal, therefore E is equal to 0. So inside a conductor electric field is always 0. No matter what is the shape of the conductor, it may be a irregular shaped conductor or a spherical conductor, no electric field can exist inside. So interior of the conductor will never have an electric field. The second point is the interior of a conductor will have no excess of charge in static situation. The charge given externally will be moved entirely to the outer surface of the conductor. This also we already discussed. So the charge given to the conductor will be automatically moving to the outer surface of the conductor and spreading uniformly over there. So this is another property of the conductor. No charge can reside in the interior of the conductor. The excess charge will always shift to the outer surface of the conductor. And the third property we are going to discuss, the electric field on the surface of a charged conductor will always normal to the surface. In another sense, we already studied this. The surface of a charged conductor is equipotential. Therefore, electric field will always normal because electric field and equipotential surfaces are always perpendicular to each other. In another sense, we studied. Now I am going to explain like this. This is the surface of the conductor of any shape. The electric field will be always normal. Now I am going to assume that there is an electric field which is not normal to the surface of the conductor. If I am considering an electric field which is not normal to the surface of the conductor, I can resolve this electric field in the perpendicular direction as well as parallel to the surface of the conductor direction. So if I am assuming that this is theta, the component of electric field perpendicular to the surface will be E cos theta, and the component of electric field in the direction or parallel to the surface will be E sin theta. Now the surface charges is inside a component of electric field. So when a surface charge which is movable externally given is inside an electric field, it experiences a force. We studied that F is equal to Q into E. Here it is E sin theta. So that means surface charges experiences a force. Under that force, surface charges will move. This happens only if electric field is not perpendicular to the surface. But no such charge movement and no such current is obtained yet. There is no such surface current. That means there will be no such electric field which is not perpendicular to the surface. The electric field will be always perpendicular to the surface. The absence of a surface current shows that electric field will be always perpendicular to the surface of the charged conductor. Now the next point is, this also we already studied, electric potential at any point on the interior of the conductor is equal to that on the surface. So if it is a conductor, the interior of the conductor, the potential remains constant and the value of that potential will be that of the surface value. So this particular term we already studied for a spherical conductor. Electric potential at any point interior was equal to V is equal to 1 by 4 pi epsilon 0 Q divided by capital R, and that is the potential on the surface also. So the electric potential at any point on the interior of the conductor is equal to that on the surface. And the next one is the magnitude of electric field at any point on the surface of a charged conductor is sigma by epsilon 0, where sigma is the surface charge density. This also I already given as a problem. We proved that the surface electric field magnitude is equal to sigma by epsilon 0 into n is a unit vector in the direction of electric field. Now the next point is electrostatic shielding. We already studied electric field inside a conductor is 0. So let us consider a conductor, and this conductor have a cavity inside. Not only inside a conductor but also inside a cavity, the electric field is 0. The cavity inside a conductor remains shielded from outside electrical influence. This is because electric field vanishes inside a cavity of the metallic conductor. This particular phenomenon is called electrostatic shielding. The cavity inside a conductor will be always shielded from external electrical influences, and that particular phenomenon is called electrostatic shielding. And there are some applications also, or there are some related things also. During lighting and thunder shout, what it is safest to sit inside a car, because the metallic body of the car act as a electrostatic shielding from external disturbances. So it is safest to sit inside a car during thunder shout, because inside a car there will be a shielding, because the metallic body of the car act as a conductor, and interior of the car act as a cavity inside the conductor. Cavity inside the conductor is always excluded from external electrical influences. Now the next one is metal shield is placed around a sensitive component of electronic devices to protect them from external electrical disturbances. So if you want to protect any sensitive component from electrical disturbance, we can keep them inside a cavity inside a conductor. We can keep them in a cavity inside a conductor, or we can shield them using a metal shield around a sensitive device. If we are shielding them using a metal shield, they will be inside the metallic conductor, and that will be protected from external electrical disturbances.